This lesson 9.1d, we're just reviewing the stuff we've done over the last couple of days on radicals, but then more importantly, just rolling in the cube roots. Okay, and you're going to want your graphing calculator. It's probably going to be helpful to have it handy if you need to do that. Go ahead and grab that. And I don't plan necessarily to do every single example, but I'm going to hit the ones that I think are going to give us the most bang for our buck, and then I'm happy to show any other ones you want to see. And of course, they're all already worked out on the answer key that's on Schoology too. Okay. So in this very first part, it's just reviewing the product property of square roots and the quotient property. You've already worked with those multiple times over the last few days, knowing that if it is multiplication or division, you can quote unquote sort of distribute that radical out to your numerator and denominator or to your factors. That allows you to simplify when necessary, rationalize the denominator, that kind of thing. Okay, so we'll work a couple of problems, but my big focus is, like I said, the cube roots. So the one thing that's going to look new today is the fact that you want to pay attention to that radical symbol and check to see if it has that little index that is indicating a different root. Right? So if you look at these examples, 1 through 4 are all square roots like we've been comfortable with. But if you're, paying attention to detail, you're going to notice number 5, 6, and 7 are cube roots, right? They have that little index of 3. The main difference is that our target list of numbers is a different set. So where I was really emphasizing a few days ago, make sure you know your perfect squares between 10 and 15, the first 10 or 15 perfect squares, and you probably have gotten fairly comfortable with that list over the last few days because we used them so much. Whenever you see that cubic symbol, all of a sudden, our target numbers are different. We're not interested if 25 goes in there or if 16 goes in there, right? I now want to know if there are any perfect cubes that go in there. And we may not be as familiar with that list, so I want to just show you or remind you a quick, easy way that you can pull up that list on your calculator. So if you grab your calculator, you can always go to this y equals right here. And for example, if a list of perfect cubes is what we're interested in, just in the y equals, just put x to the third power. And that's what it'll do. It'll take every single input, 1, 2, 3, 4, 5, and it'll cube it for you, right? So that if you put that in there and you pull up your table, there's your list of perfect cubes right there. You could do that with your perfect squares. You could do that with your cubes or any list you're interested in, any degree, okay? So what I'm getting at is when you see that cube root symbol, all of a sudden, these are the numbers we're interested in. Like I said, I'm not interested, does 4 go into that, or does 49? I'm interested in, does one of these perfect cubes go into that? And the advantage to this table is not only is it giving you a list of the perfect cubes, but it's telling you what the cube root is, right? Because on my left side, that left-hand column is the x. It's what was cubed to get that output. So that's your cube root, right? So if 7 to the third power is 343, that means that the cube root of 343 is 7. So you have them nice side by side. You know what the perfect cube is, and you know what the cube root is. So they're right there nice and handy. You could do the same thing, like I said, with x squared and pull up the perfect squares, okay, or any other root. Okay, so this is our target list for those cubics, okay, and that's the big difference. The rest of it, the behavior, what we're going to work on is exactly the same. We're going to be separating that cube root from whatever else, other factor, and we're pulling that out and we're leaving the rest in, okay. The other thing that's different about today is how we handle the variables, okay, because a couple of days ago, our root was a square root, which is a root 2. So we just wanted our exponents to be divisible by 2, right? Well, if all of a sudden we have, like number 7, a cube root that is an index 3, then I need my exponent now to be divisible by 3, right? So that's all it is. You're just kind of changing that target number, okay? So let's do a couple of examples of square roots, and if we're good, then we'll do a couple of cube roots. So let's start with number 1, right? Just because the numbers get a little bit more complex here, right? So we have negative square root of 512 h to the 7th power. First of all, the negative on the outside is like having a coefficient of -1. It's just kind of hanging out in the front. Okay. Okay, so we just have that negative outside. And really the question is 512 a perfect square? And if not, then is there a perfect square factor that goes into 512, right? And again, if that one is bigger and out of your memory bank list, right, because we know we probably have the first 10 or 15 memorized, then like I said, you could do use this same tool for perfect squares, okay? So if I do y equals x squared, there's my perfect squares. And these are probably the ones we already have memorized anyway. But let's see, it's 512 on our list. That's kind of the million-dollar question here. And I see that 512 is not on our list, right? So 512 is not a perfect square. So then comes the second piece of this, right? Are there any perfect square factors that go into this, right? And so we can test a few. And in fact, you can sometimes put this side by side. That might help. A couple of days ago, I also showed you how if you wanted to find numbers that multiply to give you something specific, that, you could just do that number divided by x. So I could even leave those two things side by side and look here on the red, right, for perfect, like factors that go into 512 and kind of compare that to what I might have over here, you know. So if you don't find that helpful, then don't do that. But I'm looking at, here's my perfect square list, and I'm looking to see if there's anything I hit. So like right there, I notice 64. 64 is a perfect square. Okay, it's on my blue list, and it also goes into 512. But here's the thing, right? 64 times what gives me 512? 8, right? Okay, so if I do that, does 8 have any other perfect squares in it? Yeah, so I might do something like that. I might say, you know what? I know that this is 64 times 8, but I actually also know that 8 is 4 times 2, and there's my two perfect squares, right? So you can just pull them, because remember, you got to pull all the perfect squares out, right? So if I get 64 times 8, head up, then I can also do 4 times 2 for the 8, right? All right, what about the h? Is that a perfect square? But what can we rewrite that as? H to the 6th power, right? You want to get the biggest even power, the one that's right, the closest one, the most you can get. So I can break that h to the 7 into the h to the 6 times an extra 1. Okay, that's my largest even number of h's that I have, is h to the 6. And then there's that extra 1 that we're just going to have to leave inside. Okay? All right, so this is a perfect square, that's a perfect square, that's a perfect square. All of that I'm going to be able to take the square root of, okay? All of it. And then the 2 and the h are the only things that I'm going to have to be stuck leaving inside. So 64, I'm able to take the square root of the 4. I'm going to be able to take the square root of h to the 6. And the negative still hanging out. The 2 and the h are the ones that are going to have to just stay, because I can't really evaluate that part without it getting to messy decimal, right? All right, what's the square root of 64? 8, right? What's the square root of 4? And what's the square root of h to the 6th? H to the 3rd, right? So we just divided by the index. Okay, and then we still have this guy in there. And last but not least, now that these are whole numbers and they are compatible, I can multiply them. So 8 times 2 is what? 16. So this gives us, and we still have that negative, and then we have the 16h to the 3rd times the square root of 2h. And that is as clean and as much work as we'll be able to do on this one. Okay? All right. Let's do one more square root. Let's try number 4. Try that number 4 on your own. See, and if that feels good, then we're going to move on from the square roots and focus on cube roots. Okay, so try 4 real quick. In your notes. Quickly. Okay. So step 1, well, because when we are taking the square root of a power, we just have to divide it by the index. What that really means is that's a good question. So that really means that when I'm taking the square root of h to the 6, we're asking ourselves, what in here got squared, right? And the power property tells us that h to the third is what would have been squared here, and those would have multiplied. 3 times 2 is 6, right? So because that power to power property says that we multiply by our power, then all I have to do is divide by 2 to get back to the original, okay? Oh, that is not an eraser. All right, so let's try this one, and if we feel good about it, we are going to go on to, there it is. Okay. Let's try number 4. So first of all, is there anything that can reduce in that fraction since they're both on the inside? 49 over 64, does anything that goes into both of those? Anything that goes into both 49 and 64? No, right? What about x and y? These are those different variables, so we can't. But that's a good thing to check for, just to be sure. That can always, a lot of times, make our work a lot easier. Okay, so then the other thing is we can't leave a fraction inside. So we'll split this up. We'll take the square root of the numerator over the square root of our denominator. Okay? And then in the numerator, is 49 a perfect square? Is x to the third a perfect square? No. Right? For it to be a perfect square, our exponent has to be divisible by, yeah, it has to be even for this one. It's got to be divisible by our index, and in this case, our index is 2. So when we split this up, I'm going to do square root of 49, and I'm going to, just kidding. I'm going to split this up into x squared times the extra x. That's a perfect square. That's a perfect square. And the bottom, though, is 64 a perfect square? Is y squared a perfect square? So that will work out nicely. So on the top, square root of 49 is just 7. And what's the square root of x squared? X, right? And then square root of x stays inside. And then square root of 64 is 8. And the square root of y squared is y. And that's it. And that's nothing else that we can reduce or simplify, so we're good. Okay, are we feeling okay with those? Can we go on to cubics? Let's go on to the cubic stuff, right? So let's look at number 5, for example. Number 5, it has that little index of 3 in that top left corner. That tells us that's a cube root. So all of a sudden, our target list changes. We're looking to see, are there any perfect cubes that go into 135, or even if 135 might be a cube, right? Those are the things we're looking for. The other thing, just a reminder, we learned this back in this fall, it is okay if there's a negative inside of a cube root, okay? If this is odd, if that index is odd right here, then it is perfectly fine for there to be a negative, because I can do a negative times a negative times a negative and have a negative, okay? The ones that I can't do are the square root of negatives. That's not any real number. But I can do the cube root of a negative, so that's fine. All right, so let's check. Since we are not as familiar with our cube roots, let's check here. Is 135 a cube root? I mean a perfect cube, sorry. Is it on our list? No, it's not. I can back up a little bit here. But 135 is not on our list. You can already see that here. And then, okay, well, then the next question is, do any of these guys go in there? Right? And so if we're not sure, like I said, it might help to go ahead and do this whole 135 divided by x and compare the lists side by side. So my blue list is my perfect cubes. My red list here is numbers that go into 135. Do you see any number that might be on both lists? Which one? 27, right? So we have 27, which we are being told right in here is a perfect cube, and I'm seeing over here that it goes in to 135 5 times. So we're good to go. I can break up 135 into 27 times 5, and then I know that when I take the cube root of that 27, what's going to be the cube root? 3, right? So there we go. We're in business. Let's do it. The other thing that comes up here, because we hadn't had to deal with it before, is who gets the negative? Who gets to keep the negative? Here's the answer. You always yank the negative out. Don't leave the negative inside the radical. So whatever perfect cube is coming out, put the negative with that, okay? So I'm going to actually separate this into a negative 27 times 5. And then, like before, we'll take the cube root of that negative 27 separately than the cube root of the 5, because I can't do anything with that. And we all agreed just a moment ago that the cube root of 27 is 3, so the cube root of negative 27 is just negative 3. So we just end up with a negative 3 outside, and then our little cube root of 5. That's your answer. Okay, so it's the same steps. It's just a different target set of numbers. We're now looking at cubics instead of square roots. Okay, let's try number 6. Cube root of 729. That's a big number. The first question is it a perfect cube? And if not, are there any perfect cube factors that go into 729? So let's visit our list. Is 729 a perfect cube? Yes, it is. You probably already have it on your list. I went a little too far on mine. So there it is right there. And not only is it a perfect cube, but I can see right away that the cube root is going to be 9, right? So if I go back to my notes, the cube root of 729, that's just a nice whole number 9. End of story. Okay? Try number 7. Try that one on your own, maybe. Okay? You've got a negative on the outside, and then you have the cube root of negative 192 x to the 5th. Okay? So we're looking at 192. I've got a negative on the outside. It's like a -1 coefficient. Let's check out and see if 192 is a perfect cube. You know what? I'm going to come here and I'm going to get rid of this other thing something. Here. Okay, so there's my cubes list. Is 192 on there? No, there's not. Okay, so then the next question is, are there any perfect cubes that are on this list that go into 192? And again, if you don't have that list of, multiples handy, maybe do 192 divided by x, and then look at those lists side by side. So I have my perfect cubes in the middle, and then right next to that I have numbers that go into 192. Do you see anything there that is a perfect cube that's on both lists? 64, right? So I notice here that 192 is 64 times 3. And I'm also being told, oh yeah, but 64 is a perfect cube. What's the cube root of 64? 4, right? Okay, 64 is one of those that's odd. It's kind of weird because it's a perfect cube and it's a perfect square. 64 is actually on both lists, so you got to be careful with that one. It can be sneaky. Okay, so, but we can break this up into a negative 64 times 3. What about the x to the 5th? Is that a perfect cube? No, right? 5 does not divide evenly by 3. So what is the largest number of x's that I have right now that is divisible by 3? 3, right? So we're going to break that up into x to the 3rd times those extra 2. Okay? Because 3 is the most that I can divide out here. Okay? All right, cool. So I have a couple of perfect cubes. Negative 64 is a perfect cube. X cubed is a perfect cube. So I'll be able to take the cube root of those guys. I should put my little cube root there. Cube. So I'll be able to do this part, but then I'll also have this other one that'll just hold those other factors that I'm not even going to try to mess with because they would make a messy decimal situation. Okay? All right, let's do this. So what is the cube root of negative 64? It is a -4. Okay, so I had kind of this -1 hanging out in front, and now the cube root of negative 64 is -4. And then what's the cube root of x cubed? Just x, right? 3 divided by 3 is 1, so it's just x to the 1st power. Okay? And then, like I said, the other radical, cube root of 3x squared, that's just going to stay inside. Okay? And last but not least, what happens when I have a negative, and then I have another times another -4? Positive, right? So finally, our answer here is 4x, and then times the cube root of 3x squared. And that's our final solution. Okay. Try number 9 on your own. Okay, just try that one out, and if we feel good, like I said, I'm going to skip through unless y'all want to see some of those. I'm going to skip through a little bit. Try number 9, and if you feel good about those, then we'll talk about rationalizing denominators with cubics, and we'll finish out with that. Okay? So And I'll give you a big hint on number 9. Remember, it pays off a lot of times if you simplify anything that can be simplified before you get started. Okay, so if you look at number 9, is there anything in that fraction that can kind of reduce or cancel or simplify? What? X to the third over x to the third. They're identical terms, guys. They're exactly the same thing over itself, right? So since they're both radicals, they are compatible, and I can just reduce this. I can say, you know what? Anything over itself just cancels. That already made my life a lot easier. I don't have to worry about, you know, the exponent, if it's divisible by 3 or what I need to split it up. That's just less work. That's awesome, right? What about 8 over 27? Does that simplify? What goes into 8 and 27? No, that doesn't reduce, right? So the next step is just to separate this out and take the cube root of 8 separately than the cube root of 27. Okay? And since it's cube roots, the question is, are 8 and 27 perfect cubes? Yes, they are. They both are. Okay? Luckily, both of them are perfect cubes, and there's their cube roots right there, 2 and 3. So that makes life even better. The cube root of 8 is 2, and the cube root of 27, 3. And that does not simplify further, so we are good to go. Okay? Give me some thumbs up, down. How do we feel about those cube roots? Okay, so? All right, most of yours. All right, let's talk about rationalizing denominators. See what that looks like a little bit. Look at 11. On number 11, you've got 8 over cube root of 16. 8 is already a whole number. So I can't really simplify it with a 16 like I did a moment ago with those x's because these are not compatible. I have a whole number 8, and then I have the cube root of 16. I don't have 16. I have the cube root of 16. So those are not compatible. I can't do that, a whole number with a radical. Just remember that. All right, but I need to get rid of that radical in the denominator. Okay, I can't just leave my answer like this and be done. I cannot leave radicals in the denominator. So we need to rationalize the denominator like we did yesterday. And that means that essentially I need to figure out something to multiply this by so that I get a perfect cube. That's how I clear a radical. I get a perfect root for that. Okay? So if I have cube root of 16, which is not a perfect cube, okay, I need to figure out what could I multiply 16 by and get a perfect cube. So let's take a look at our list, although I already heard the right answer here, which is good. Y'all are already thinking ahead. If I look at my list of perfect cubes, 16 is not on there, but which of these does 16 go into evenly? No. Which one does 16 go into evenly? 64. 16 times what? What would I need to multiply 16 by to get a 64? By 4. Okay, so there it is. So I'm going to say, okay, well, if I multiply it by a 4, 16 times 4 will give me a 64, and I will have a perfect cube in there, and then I can take the cube root. That is how we clear the radical. We create a perfect root that we can actually take the root of, and that's how we can clear it, right? But of course, if we do it on the bottom, we also have to do it on the top, right? So that'll give us that up there, which will just be 8 times the cube root of 4, okay? But on the bottom, most importantly, I have a perfect cube, and I can evaluate that. What's the cube root of 64? 4. So now I have 8 times the cube root of 4 over, and then that's now just a whole number 4. And my goal, successful. I got rid of the radical in the denominator, okay? Anything else that we can simplify? Yes, what else simplifies here? 8 over 4, because now those are whole numbers. Both of them are outside the radical. They're whole numbers. They are compatible. We can reduce them. 8 over 4 is just 2. So we end up with this as our final answer, because this right here is just 2. Okay? Yes? The cube root of a half, but you could, but then you're going to end up with that on the top too. Then you'll have to simplify that because you can't leave fractions in a radicand. And so, you know what I'm saying? Like, you would achieve your bottom, but you would kind of create some new problems on the top. So it's just easier to find your multiple. Yeah. No, we won't throw that at you. Yeah, but they'll be like this. Some problems will be one or the other. So as you're going through the questions on the quiz or whatever, make sure you're looking to see what the index. But we won't put like the two different indexes in the same like question. Okay. Good question. Okay, let's take a look at number 12. Let's just try these last couple ones. Number 12, you've got 2 over the cube root of 9. There's nothing we can really clean up with that 2 and the 9, but we have to rationalize the denominator. So once again, 9 is not a perfect cube. If you look at your list, you're going to notice it's not on there because 9 is not a perfect cube. So the next question is, what could we multiply here to create a perfect cube? So which of the perfect cubes does 9 go into? 27, right? What could we multiply 9 by to get 27? 3. Boom. There it is. Mission accomplished. We will multiply by the cube root of 3 on top and bottom because that will create a cube root of 27, which we will be able to solve or evaluate, right? So on the top, I'll just get 2 times that cube root of 3. But more importantly, on the bottom, I have cube root of 27, which is a perfect cube, and we're in business, right? So 2 cube root of 3 in the numerator. In the denominator, what is the cube root of 27? 3. Anything else that we can do here to clean this up? No, right? 2 over 3 doesn't reduce or simplify. There's nothing else I can do here. That's your answer. Okay? Try 13. And that'll be kind of our checkout one. You can see all the other ones on the answer key. But unless y'all request it, I'll leave it at this. Try 13 on your own. Okay, so the first thing that we have to realize should kind of bug us is that there's a fraction inside. That's a deal breaker. So we do have to distribute out our cube root to the numerator and the denominator. What happened there? Okay, now the top is easy because the cube root of 1 is 1, right? 1 is a perfect cube, and the cube root of 1 is 1. So that does simplify to just 1. On the bottom, though, the cube root of 243 y squared, you can check the list, but I'm pretty confident that neither of those are perfect cube. Well, I know y squared isn't, okay? And I know 243 is not a perfect cube either. So we're going to have to do what we did on numbers 11 and 12, okay? Let's do the y first. That's easy. I have 2 factors of y. How many do I need for a perfect cube? 3. So I just need to add, multiply in how many more? 1. So I just need 1 more y. Got it? Okay? So we'll definitely do that. Okay? Cube root, we'll definitely multiply in 1 more y. And then the question is 243 times what would give me one of these guys? Okay? And when I think about 243, I kind of know 24 times 3 is 72, and I know 3 times 3 is 9. So I'm thinking it goes into 729. You can test it. You can check it. Okay, you could pull up the factors if you want. But yes, 243 times 3 gives me 729, which is a perfect cube. Okay, so I'm going to come back here. I'm going to say, you know what? Let's make this a 3. That'll do it. So cube root of 3y. Okay, and when we do that, we end up with cube root of 3y in the numerator, because that times 1 is just the same thing. But in the denominator, I get the cube root of 729 y to the 3rd, and that whole thing is a perfect cube. And we can take the cube root of it and get rid of the radical. So and I have cube root of 3y. Okay, sorry for a glitch there. So on the top we get cube root of 3y. On the bottom, this comes out to just 9y. And that is as far as that goes. There's nothing else we can simplify. And that is a fully simplified answer.